Global Navigation Satellite Systems, or GNSS, provide air navigation around the world, from highly integrated systems in airlines to handheld receivers in ultralights. Most people associate GNSS with GPS, the US government's satellite constellation. But things are changing. Soon the European Union's Galileo constellation will come online. The good news is that the two systems are going to work together, making it even more reliable. There's also a third system, GLONASS, run by the Russians. In this program, we'll look at how GNSS works and what we've learned over the years about human factors, VFR and IFR operations, and how the next generation of GNSS receivers will improve IFR navigation. But let's start with the rocket science. There are three elements to a GNSS system. First, there are the satellites, a minimum of 24 in the case of GPS, in 6 orbital planes about 11,000 miles above the Earth. And each one of them is transmitting GPS signals. Second, there's the GPS receiver giving the pilot positioning, velocity and precise timing information. The receiver compares the ephemeris data transmitted from the satellites with its own almanac information. Finally, there's ground-based control, a network of monitoring stations that checks the accuracy of the satellite positions and their atomic clocks. The GNSS works out a navigation solution for an aircraft from the differences in the time of flight of the radio waves from the GPS satellites to the receiver, and it takes 4 satellites to tell you where you are. However, the system does have errors. Solar radiation and the gravitational pull of the Earth and Moon can cause wobbles in the satellite's orbits. The satellite's atomic clock can go haywire. And the ionosphere, a layer of charged particles about 200 kilometers from the Earth's surface, can slow the radio signals down, skewing the position and time information. And there's selective availability, the unit's built-in paranoia, a deliberately introduced error to stop hostile forces using the system against the United States. It's now switched off, but the old receivers don't know that and factor the error in. All of these errors tend to amplify or cancel each other out depending on the geometry of the satellites, but they limit GNSS accuracy to about 15 meters. There's a big difference between aviation and non-aviation receivers. Aviation receivers are certified according to a TSO or Technical Standard Order and fitted according to a CASA advisory circular. Uncertified units have no way of detecting errors. Unbelievably, they can be out by more than 500 nautical miles, and they don't meet any of the requirements for IFR navigation. IFR requires a RAM-capable receiver, either a TSO C129 or C145A or 146A. And what's RAM? It's Receiver Autonomous Integrity Monitoring, and it's how the system maintains integrity by warning you there's a failure in the navigation system. RAM in C129 receivers monitors and compares data from 5 or 4 satellites and the aircraft's pressure altitude equipment. This is known as fault detection. Sadly, if it detects a faulty satellite, it can't knock it out of the equation, and the receiver becomes as helpful as a house brick, so you're forced to navigate by other means. The new TSO C145A and 146A receivers are far better as they have fault detection and exclusion, or FDE. This means they can not only detect a faulty satellite, but eliminate it from the calculations. And they're more like a flight management system with more user-friendly interfaces and improved computing. They don't factor in selective availability, and they keep on working at times when the old units tell you the system is down. During flight planning, it's important to get a rain prediction NOTAM from Air Services, and they've expanded their service to include the new and old receivers. The prediction precisely forecasts RAM holes or outages, times when there are too few satellites in the right place to give you service. For example, if you plan to fly to Canberra and do a non-precision approach and the RAM prediction service forecasts an outage between 10 AM and 10:20 AM. You can plan around these times to conduct your approach. But if you blast off thinking the onboard receiver will give you the same prediction, you're wrong. Your receiver doesn't know about the predicted outage and will only find it when you're nearing Canberra, or worse, when you're halfway through the approach. Remember, there's a big difference between an outage and a RAIM warning. A warning is when RAIM has detected a satellite fault, and an outage is when there are too few satellites for GNSS navigation. Pilots have taken to GNSS like teenagers to mobile phones, and it's used in 85% of Australian registered aircraft. In IFR operations, you must be qualified in GNSS before you can use it. You have to do ground training based on a syllabus set by CASA at an approved training and checking organisation or an instrument school. It's vital you know what type of receiver you're using, as they're all different. For instance, not all C129 receivers meet the requirements for non-precision approaches, and they can't take advantage of advanced GNSS capabilities. Check operating manuals, know your equipment and know how to use it. Be well aware there are currency requirements if you want to do a GNSS RNAV approach. Night VFR RNAV pilots must hold the appropriate GNSS qualifications and only use aviation-approved TSO C129 or TSO C145A or 146A receivers. For VFR, there are no minimum requirements, but pilots are encouraged to become familiar with the equipment and carry operating manuals close at hand. But VFR charts should remain the primary reference for navigation. GNSS works on the gyro, garbage in, rubbish out principle, so take care with data entry. The interfaces in the new receivers are more user-friendly, but training and familiarity are still critical. Button pushing can increase workload, especially if you're trying to learn in flight. It can distract you from other tasks and compromise your ability to make decisions. It's a good idea to get around the technology on the ground, and most GPS suppliers have simulators you can download from their websites. Know the receiver's modes of operations and warnings, especially messages and annunciation it gives en route and during a non-precision approach. Databases must be current and provided by an approved supplier. Manually entered data should be cross-checked for accuracy by 2 flight crew members, and when operating alone, verify against current maps and charts. Do not attempt to design your own approach. Approach designs are created by experts, and there are many levels of validation before approval. Never ever deviate from a designed approach. Check outputs are sensible and don't fly below published minimum altitudes while in IMC. Pilots have crashed using the wrong procedures. And remember, non-aviation based receivers, including handheld units, can have huge errors. And don't forget how to navigate the old-fashioned way. GNSS junkies often lose critical aviation skills through lack of use. So what's next? Well, there's good news if you have an old C129 receiver, as some of the manufacturers have promised to upgrade to a TSO C146A standard soon. Not too far away are vertical guided approaches, or APVs, and the new C146A receivers are already APV capable. Furthermore, satellite navigation is about to get even better with new augmentation technology. Augmentation corrects the errors in the GPS system using a range of technologies. SBAS, or satellite-based augmentation systems, use dedicated high-orbit geostationary satellites to get ranging, integrity and correctional information from a GNSS ground monitoring network. SBAS satellites transmit the data to the aircraft. It promises approaches with vertical guidance, and Australia could get SBAS services from the Japanese MTSAT geostationary satellite constellation and the US WAS systems. All of the new TSO C146A receivers are WAS capable, but Australia doesn't have the ground infrastructure to support WAS. GBAS, or ground-based augmentation systems, deploy a ground station at the airport to monitor GPS satellites and transmit corrections, integrity parameters and approach data through a VHF uplink on board the aircraft. Then there's ADS-B, or Automatic Dependent Surveillance Broadcast, a high-performance surveillance system likely to replace radar and being rolled out around Australia. More and more technology to tell you and ATC where you are and where you're going. So let's have a recap. Remember, aviation GNSS receivers meet strict technical standards, far above non-aviation units. Know your receiver and its capabilities. Always get your rain predictions from Air Services. Thoroughly cross-check manually entered data. Never deviate from designed approaches. And for VFR, maps and charts are your primary means of navigation. So there you have it. Go find yourself.